Hello everyone, welcome back to my tutorial. In this tutorial, we are going to solve this thermomechanical analysis of a bar which is 1 meter length and 0.1 meter breadth and 0.1 meter height. It has a made up of steel with Young's modulus 210 gigapascal and Poisson ratio is 0.3. Thermal expansion is 12 e power minus 6 1 by Kelvin is the unit. Density is 7860 kg per meter cube and thermal conductivity is 40. So density is not required for this case. These four properties required to solve this thermomechanical analysis. Now we will see the boundary condition. Here both the side, this face and this face are fixed in x direction, y direction and z direction, and it has a temperature difference of here 100 degrees Celsius and here 200 degrees Celsius. As here thermal expansion is in Kelvin, so now we just want to input this temperature also in the Kelvin. So the converting is 273 plus 100 is equal to 373 Kelvin. Similarly here also 273 plus 200 is equal to 473 Kelvin. Now we will solve this case using Salome. So as I have opened the Salome, it has a different models. Now we'll see one by one. First go to geometry model to create the geometry. Now I just want to model this simple bar, a rod of 1 meter length and 0.1 meter height and 0.1 meter width. So for that we can create by from the basic. Also from that point we'll create a line, then we'll create a 2D sketch, then we'll build a face. From that we can generate a solid. That way also we can generate. Now I'm going to create by using primitives box. Here like dx is 1 meter and these two are 0.1 and 0.1. Now just giving a fit screen. This is our object, directly we can create. Then we just give apply and close. Now we'll create a groups to apply the boundary condition. Now we have two groups. Here you can see fixed 1 and fixed 2. Anyway both the groups are fixed in all the direction. So I'm just going to create a single group. Here this face just add it here and this face just add it here. Both the surface number is coming here. Just name it as fixed. Just apply. We can create volume group also. Just apply and close. So this is we are going to use. This is not required first. Now we will save this file. Go to file, save as, pictures, code aster, the first case, and saving it. Now we'll create a mesh. Just go to mesh model, select this box one, mesh, create mesh. Here there are different algorithms are there. In this case I'm going to use hexa element, hexahedron. In 2D it has to be a quadrangle. In 1D wire discretization, I am controlling using a local length 0.02. Say OK, apply and close. Now right click this mesh one, compute it. Now I have created linear element. See, hexahedron element I have created. Now I'm just saving this file. So now we have created a geometry, then we have created mesh. Now we move into aster study to create the setup. So move to aster study, stable version, save OK. Here you can see, now we have to solve the thermomechanical analysis. First we'll do the thermal analysis by applying the temperature in here 100 degrees Celsius, here 373 Kelvin and here 473 Kelvin. After solving thermal analysis, we'll impose the results into the geometry and we'll do the mechanical analysis. In mechanical analysis, we are not applying any loads, we are just constraining these two phases. In thermal analysis, we are applying a temperature difference. What it will do, it will expand due to the temperature difference. So due to the temperature difference, it will trying to expand. But in mechanical analysis, we are arresting the expansion. Due to the arresting of expansion, it will generate the stress. So that stress we are going to calculate it. Okay. First we'll do the thermal, then it will do mechanical. So that way also we can, that is the way we are going to do. Now to create the setup, what we are going to do, we are going to use assistant. Add a stage with assistant. Here you can see thermomechanical analysis. So just go to next. Here mesh 1, this is a 3D mesh. So here we have to specify the thermal property as well as the mechanical property. Conductivity is 45. Young's modulus is same. Poisson ratio also there. Thermal expansion is 12 e power minus 6. Volumetric capacity is not at all required. To do the transient analysis only, volumic heat capacity is required. This is nothing but density into specific heat. Now I'm just giving a 0. This is no long. This value is not going to take for solving thermomechanical analysis. I'm just giving next. First impose the temperature on the groups. Actually we have a two temperature values. For that we have to create two different boundary values. Here I am going to create fixed 1, fixed 2. Then only we can apply separate temperature and 373 Kelvin and 473 Kelvin separately. So for that I'm just going to click back, cancel it, go to geometry again. Here delete this face. Here also we will be having a face. Delete this face. Now go to geometry model again. Create a group. This one is the phase 1. That is fixed 1. And this one is the phase 2. Fixed 2. Just apply and close. This is the way we have to create. Then just import this mesh group by using create a group from geometry as an elemental group. Just apply and close. Two mesh group I have taken. We can check these groups. Yes, which is correct. Now just go to aster study again. Now just go to the same location, add a stage with assistant, thermomechanical analysis. Here you can see simply in thermal analysis we can give imposed temperature, that means fixed temperature groups. Normal stream is nothing but heat flux, and volumetric stores means volumetric heat generation also we can give. This is surface heat flux, this is volumetric heat flux. This two only we can give, this three boundary condition. In mechanical analysis we can apply pressure and we can block the displacement. This two boundary condition only we can apply using wizard, that means assistant. And mesh is 2D and 3D mesh we can use it. Okay. If you want to apply any other boundary condition means we have to edit or we can do by step by step by adding the stages, then we can do that one. So now just go to next. This is a mesh one. Next, 3D. This thermal conductivity is 45. Here see the 40. This is same only 0.3. Thermal expansion is 12 e power minus 6. This is not required. Just go to next. Impose temperature fixed one in 373 Kelvin and fixed 2 which is in 473 Kelvin. Next, no normal streams. Go to next. No volumetric streams. Now initial temperature it is asking. We have to specify initial temperature in Kelvin only. It is an initial temperature of 273 Kelvin. Initially it is in the atmospheric temperature which is 293 Kelvin. Almost at atmospheric temperature 20 degrees Celsius. I am taking 273 plus 20, 293. Next, enter time step it is asking. We can solve it by using a time step also. Now I'm not going to do with this time step, so just leave this one. Now it is started mechanical conditions. Now we can apply the boundary conditions. Fixed 1 and fixed 2 both are fixed in all the direction. Now there is no pressure load, but anyway we have to add the pressure load. Then we'll remove it by using after generating the command. Now we'll save this file. Finish. Now we'll check this command file one by one. Now see, we are reading the mesh. Then this one is the thermal model and this one is the mechanical model. Thermal model, mechanical model. Material is a complete material. Rho CP is not required. If you want to remove this also, we can remove it. Rho CP I am removing it. That is not even required. See here. Then we are assigning the material property to the model. Then here you can see defi list real. This is not required. I'm just deleting this one. Then boundary condition. So one side is 373 Kelvin, another side is 473 Kelvin. This is the thermal boundary condition. Then mechanical boundary condition, one side, both the side we are fixing. Then pressure, which is not required, just delete it. Then thermal solver, these two are not required. Initial condition and time stepping are not required. Just OK. Then material, here mat meca. Here you can see the reference temperature is 293 Kelvin. What it will do, this condition, this FE material, whatever it is solving the thermal problem, that result will, data will be imposed to the model. So here you can see thermal result will be imposed to the model. Just OK. With the reference temperature of 293 Kelvin. Then we have to do mechanical solver. In mechanical, time stepping is not required, and here pressure value also not required. This also we can remove. Just apply and OK. Now what it will do, it will calculate on the displacement. Then we have to calculate the stress value. For that, just go to post processing, call champ. Here we choose this one, constraint and criteria. Here choose sigma elemental and sigma nodal. Sigma LNO, sigma nodal, as well as here SIEQ LNO, SIEQ nodal. Just apply. Here use the same name, just apply and OK. Now here output, we want the thermal output as well as the mechanical output. In result, first one is thermal output, result thermal, result meca, you change into second called champ. Here there is option called tau champ, make it S. Then you just say OK. Then you just apply and OK. Now see, everything is correct. There is no red color indication. Now commands are correct. Now we'll solve this case. Just goes to history view. Just click this run. Here make it 5 seconds. I'm just giving some more memory, 4048. Just run it. Just wait for a while. It will solve thermal first, then it will solve the mechanical. The thermal value will be imposed to the model, then it will apply the constraints. Then it will calculate the stress due to the temperature difference. Now it is solved without any error. In message file also we can see it here. It is diagnostic job is okay. We can open by using this also. So this one is the message file, it is showing there. Now we can open the result file using a paraview to do the post processing. I'm just opening using paraview. Just right click this built-in, just open it, go to home, pictures. Now just go to the location where your case is there available. Now my case is 77. The result file name is thermomec.rmd. Just select this file, save OK. Now you can see it here. There are two results. One is comp sub 0, comp sub 0. This is the first TS0 and TS1. Two result files are there. First one is temperature file. Just select here, just apply. We can see the conduction out, the temperature difference. Now I'm going to show this result using rainbow and this value in 12. So the temperature value is one side 373 Kelvin. The blue color is 373 Kelvin and the red color is 473 Kelvin. Along this the conduction is happening because we have specified the thermal conductivity of this material. And external temperature is 293 Kelvin. Now it is showing only one value after the digit in the starting and end the value. To change the digit value, here you can go. Here there is a range label format. Increase this 1 into some 4. Just apply and OK. Now we can see 4.73. This way we can see. This is one of the way. The another way is make this E instead of E, F you can give, just apply. See, this way also we can see it, just say OK. So after that point it is showing 4 digit, that is a 4 we have given. To show the full value we can give F. So 473 and 373. This is the thermal value which is correct. Whatever we have specified, it is solved in the correct way. Now we will check the stress values. Now just select this one, apply. Now just see the displacement. This is the displacement magnitude. Now we just want to see the displacement in X direction. In the both the direction here and here we are fixing it. That's why it is showing minimum value of 1 e power minus 5. Due to the temperature difference, it is elongating. Here we are getting more displacement. Now we'll see the stress. In x directional stress, we are getting this much. Sigma xx is, we are getting maximum of this value we are getting here. That is because we are constraining here. Away from this location, you can see the stress of minus 1.4 e power 8. That means 140 megapascal, which is in the compressive nature. Similarly, we can see the von Mises stress. So von Mises stress, we are getting the same of around here, around 338 megapascal. Here we are getting 338 megapascal. So here only we can see the which is in the compressive nature or in the tensile nature. In sigma xx, it is showing minus 1.4 e power 8. That is means it is in the compressive nature. Okay. Now we can see the deformation of this body using a wrap by vector. I'm just giving some more scale. Just apply. Little apply. So this is the way it is going to expand. Here you can see, here temperature is less, the expansion is less. Here the temperature is more, the expansion is more. Now we can animate this also. Create a new animation track. So I'm just changing this color into blue to red. That will look good. Now we'll animate this by using animation track. Just create a new animation track. Some 20 frames I'm giving. Just save OK. Now we can animate it. Scale is more. It is. Make it loop. So this is the way it is going to animate. This is the way it is going to expand. So in this case, we have solved thermomechanical analysis of fixed beam or fixed bar in temperature, in temperature difference. So thank you for watching my videos. Please subscribe my channel for more videos. Thank you.